So now let's look at the host network. And if we look at this page, the thing I want to highlight is this bit. The host networking driver only works in Linux hosts. Now, we've already seen us use it a bit for the integration tests. The thing I want to highlight there is we weren't using it for anything outside of Docker, outside of Linux, because I'm using Docker for Windows, which is using WSL2, which is Linux. So in that example, I had SQL Server running in Docker, and I was doing Docker build, which was running the integration tests, which were using localhost. So it could run the same from Rider against that database in Docker, but also use localhost when doing the Docker build, which is also from Docker. But because of all of that is running in Linux, then this issue didn't come into account. But to demo this properly, I'm going to switch it over to Linux now. So this is Ubuntu just running in a VM, and it just means I can show you how this works properly. So I've got Nginx running. Now Nginx isn't running in Docker, it's just running over here. So if I do systemctl stop Nginx, and then try and run it again, it's gone away. And if I start it again now, so this is just on the host. And it's back again. So now I'm going to spin up a Docker container. So the usual -it, so I'll get an interactive terminal, rm, so when we exit it, it goes away. And I'm going to use an image called curl. So curl image is curl. So this is just because Alpine doesn't have curl in it by default. So I'm saving myself an apt-get. And, oh, actually I need to do the sh because we want a terminal. So now I can do curl localhost. And this can't connect to it because this is trying to find localhost inside the container, and Nginx isn't running inside this container. So if I exit out now and make a small change, I'm going to add network host. And now if I do curl localhost, we can see it's returned the HTML from this. So the container has managed to connect to Nginx as if it was running locally. And that's the point. Nginx, even though the file system in the container is isolated and the other stuff, the network isn't. It's as if you're running Nginx locally. So if I try and now do docker run -rm -p 8080, so we're binding up port 80 on the host, 80 inside, because that's what Nginx listens on, and do Nginx. So I'm trying to run Nginx inside a container, but it can't because this is using it. But I'm not using the host network, I'm saying -p, I'm explicitly binding it. If I switch this to, let's say 123.4.80, then that's going to work because even though, let's get that command up again, even though the container is still listening on port 80, we're exposing it on a different port, so that's okay. However, if -p doesn't make sense when you use network host, by the way, because the container doesn't have an IP address, it's just using the host network. If I do that, we can see that that's failing because the port that Nginx is listening to, so inside the container, is already used on the host because it's all shared. So a container running on the host network would have to have that port, the container port, available on the host, if that makes sense. So now if we stop Nginx, if I could type my password, there we are. If I stop Nginx, so this isn't working. And if I get that up now and I run Nginx, but on the host network, so I don't need to specify the port here. So this is, even though this is running in the container, it's just like I was running it outside of the container. So if I refresh this now, it looks like the container version of Nginx uses dark mode, which is quite nice. So we can see that we're using a different version, but this is the one running inside the container. But I'm still using localhost. I'm still using the implicit port 80, but I can connect to it as if it was just locally on my machine, and I didn't have to do a -p or anything. So whilst there's probably not that many times that you need to jump to this, it's very useful to know because you probably will hit times where you're developing and just a use case comes up where you're just using Docker for something and you just want it to be connecting to local services, just like it was an application running outside of Docker. So in the last section, we showed how to use the host network to allow software running inside a container to talk to stuff running on the host, like SQL Server or whatever it is, and vice versa. But I did say that this only works in Linux. And this is actually super useful in a lot of cases. And I'm guessing a lot of you probably aren't using Linux as your main OS, but that's okay because Docker does add this. When you install Docker Desktop, it adds this DNS entry into your host file. This works on Windows, Linux, and Mac. And from inside your container, you can access your host stuff using this DNS entry. So it's a really nice workaround. For example, if on my machine I had SQL Server running outside of Docker, but I wanted my containers to be able to do almost like local host to access it, instead of doing local host, it would just do host.docker.internal as the DNS name, and then it'll be able to access SQL Server running on your host machine. So that's quite a nice thing to know. So we've now covered the main network types I think you'll need to use. So the default network, which is a bridge network, but when you use Docker, you get that out of the box. That's just what happens. You've got a custom bridge network, so it's also a bridge network. For both of these two types, the containers get their own IP addresses. And for these bridge networks, both the default and the custom bridge network, each container gets its own IP address. And with the custom one, you get a bit more DNS service discovery stuff. And we've also seen that Docker Compose uses custom bridge networks by default, and you can specify some YAML in your Docker Compose to customize the network even further. Then we've got the host network, which is just like running this software in that container on your host as far as the network's concerned. So it just becomes some software running on your host, so we'll share the ports. In that case, for the host network, the container does not get an IP address. And with some other network types, which I've been using Docker for many, many years. As a developer, I've just never had to use them. So I feel this is out of scope for this course because this is a course for developers. But I'm going to highlight what we've got. So if you go to docs.docker.com and you go to networking, then this lists out the types. So we've got the bridge, which we've already seen. We've got the host we've already seen. We've got none, which just means the container doesn't have a network, so it's isolated. We've got MAC VLAN. So this basically means that each container gets its own MAC address. It's kind of like the container's plugged into your router. It gets its own MAC address. But the problem is that, as mentioned here, it's kind of the equipment needs to handle something called promiscuous mode. And this is because the containers are running on one machine, your machine, and your gear might not be able to handle multiple MAC addresses from the same physical interface like your computer. IPVLAN kind of gets around this issue. I think there is a diagram in this one, and you can see that each of the containers have an IP address matching the network router's subnet. But this doesn't have the MAC address limitation. But as I say, this kind of stuff is out of scope of this course. The documentation here is really good. So if you need to dig further, this is the best place to go. And lastly, we've got the overlay network, which the first sentence, the overlay network driver creates a distributed network among multiple Docker daemon hosts. And it's talking about using Docker Swarm, which we've already said earlier in this course. Docker Swarm is out of scope of this course because another container orchestration tool has kind of won the war for running containers in production on Kubernetes. And so we're not going to talk about Docker Swarm. But yeah, if we're talking about distributed networks of Docker daemon hosts, then as a developer, you're probably not going to need to touch this stuff. So we're coming quite close to the end of this course. We've covered a lot of content, but obviously we can't not have a section on security because that's such an important topic, and quite often people leave it till it's too late. So we definitely want to cover that in this course, which is what the next section will be. So let's talk about everybody's favorite topic, security. Security is obviously a huge topic, but thankfully, because this course doesn't cover hosting, as you'll probably be using something like Kubernetes or a cloud provider's container solution, that dramatically reduces the scope of what we need to cover in this course. Within the scope of this course, one of the main areas we need to talk about are the images that we build, as regardless of whatever container orchestration platform we go with, it'll be creating containers from these images that we've learnt to build in this course. As with all software development, keeping dependencies up to date is very important. So in your project, this includes NuGet or NPM packages or Maven or whatever package management tool your programming language of choice uses. It also includes external dependencies that you call out to, databases, third-party services. And it also includes the OS your software is running on. And in the case of Docker, the OS is the base image that you specify in your Docker file. So you want to make sure that those are also using the latest base images to protect against newly discovered vulnerabilities that have been fixed in newer base images and its dependencies. As software developers or teams of developers, we should certainly have practices around making sure that we're keeping things up to date across all of those different types of dependencies. But thankfully, on top of those practices, there's also tools that can help us along the way. In the first section, we're going to talk about tooling that's part of Docker that will scan our images for known vulnerabilities. So let's have a look at image scanning. So if we go to the command line and type docker scan, then we can see that there's an error message saying this has been removed and replaced with Docker Scout. So Docker Scan used to use a tool called Snike, I think that's how you pronounce it, but Docker's now moved to their own one called Docker Scout. But if you still wanted to use Snike, you can, here they've got their own CLI tool, but we're going to look at Docker Scout. So if we run Docker Scout now, then we can see we've got various options. So we can compare two images. We've got CVES, which stands for Common Vulnerabilities and Exposures. And this is basically a database of common vulnerabilities and exposures. So if we run that command again and type CVES, then we get a bunch of output. And actually, if we do CVES help, then we can see that if we just do that, it's scanning the most recently built image. But we can specify a particular one. So actually, this example says Alpine, so let's do that. And we can see that's green, so that's good. Now, I happen to know that an older version of Alpine, which one was 3.15.7, does have vulnerabilities. So if we run this, then we can see that there's some high ones here. And we've got the hyperlinks. So if I copy one of these and then go to the browser, then we get a lot of information about that particular vulnerability, including advisories, various information here. Docker Desktop, the GUI that we've looked at a few times, if you go to the images section, we've actually got this built in. So if I go to the latest Alpine, then you can see it said no vulnerabilities. If I go back to that 17.5, no, it wasn't that one, it was 15. 15.7, this one. Then we can see that we've got maybe a nicer way of exploring that information. And again, we've got hyperlinks to the page with more details. So if we have a look at, let's find the Dome Train API that we did earlier in this course. And we can see this has got a bunch of yellow. There's nothing red. And these are all Debian. So these are all in the base image. And there's this checkbox here, fixable packages. So this looks into the CVE database to find out if that vulnerability has been marked as fixed. So if we click on this, none have been marked as fixed. So there's probably not that much we can do about that. And also these are, so our base image is the .NET runtime, which is then using Debian as its base image. So in a way, there's not that much we can do about it. If we really wanted to upgrade these and we knew there was a later version of Debian OpenSSL, then in our Docker file, we could always update it with an apt-get or something. But it's also important to note, I wouldn't panic over this because lots of these might be exploitable if you're already in the container or in a certain scenario. Generally, to get to the code in your container, there's a whole bunch of layers of defense. But this is a really good guide. And this fixable packages is really handy as well. So because there's a command line tool, then you can run this as part of your CI/CD pipelines. And if let's do the help thing again. There is an only fixed argument which matches what we saw in the Docker Desktop GUI, that checkbox. And you can output the report to a file. So in your CI/CD pipeline, if you wanted to dump it as an artifact to attach to your pipeline, to your build, you can do. And there's various different options as well. So given how simple this is it's built into Docker and we can just run it, it certainly makes sense to include this as part of your CI/CD pipeline. And it really just emphasizes the importance of keeping everything up to date.